Hello everyone, my name is Honesto Pardede. I am mechanical engineering student from Udayana University, and I'm here to represent about metallurgy in testing and inspection of metals, the quest for quality. Here we got the references from Metallurgy for the non-metallurgists, second edition by Arthur C. Reardon. For the content, we got 7.1 metallography, 7.2 hardness testing, 7.3 tensile testing, 7.4 fracture toughness, 7.5 impact testing, 7.6 fatigue testing, and 7.7 non-destructive testing. Let's jump to first one. We got 7.1 metallography. Metallography is the scientific discipline of examining and determining of constitution and the underlying structure of the constituents in metals and alloys. The examination of structure may be done over a wide range of length, scales, or magnification levels, ranging from a visual or low magnification examination to magnification over 1 million times. With electron microscopes, metallography may also include the examination of crystal structure by techniques such as X-ray diffraction. For first figure, we got figure 7.1, the micrograph of the Elbogen iron meteorite prepared in 1808 by Count Watsmanstatten and Scribers using heavy etchant and nitric acid. After rinsing in water and drying, printer's ink was rolled on the etched surface and the sample was pressed into a piece of paper. In 7.2, we got Jose Ramon Viela, distinguished metallographer who understood the need to faithfully prepare representative surfaces in metallographic examination. And in figure 7.3, we got an example used by Viela to illustrate the effect of this disturbed metal on the appearance of pearlite. We got two figures there. In A figure, we got polished surface covered by a layer of disturbed metal, and B, the same field after removing the layer of disturbed metal by alternate polishing and etching, revealing the true structure of lamellar pearlite etched in pearl rigid, original magnification. Next, we got 7.2, the hardness testing. Hardness, as the term is used in industry, may be defined as the ability of a material to resist permanent indentation or deformation when in contact with an indenter under load. Generally, a hardness test consists of pressing an indenter of known geometry and mechanical properties into the test material. The hardness of the material is quantified using one of a variety of scales that directly or indirectly indicates the contact pressure involved in deforming the test surface. In figure 7.4, we got dual specimen mount for sample holder. Hardness testing is perhaps the simplest and the least expensive method of mechanically characterizing a material because it does not require elaborate specimen preparation, involve rather inexpensive testing equipment, and is relatively quick. There are some fairly accurate quantitative relationships between hardness values and other mechanical properties of materials, such as ultimate tensile strength and strain hardening coefficient. Hardness testing also is one of the few non-destructive tests available to qualify and release finished component for use in the intended application. Macro hardness testing. Macro hardness tests are commonly performed as an integral part of quality assurance procedures. In macro hardness testing, load exceeds 1 kg or 2.2 lb, and the resulting indentation is visible to the naked eye. Brin H test. The setup for Brinell test is shown in figure 7.5, which I also make there. The Brinell indentation processes. We got two figures there. A figure is schematic of the principle of the Brinell indentation processes, and B is the Brinell indentation with measuring scale in millimeters. Next we got figure 7.6 is a Rockwell hardness indentation. We get two figures there also, is A minor load and B major load. And figure 7.7 is a Rockwell indenter. We also get two figures there. A is a diamond cone rail indenter, and B is comparison of old and new US diamond indenters. The angle of the new indenter remains at 120 degree, but it has larger radius closer to the average ASTM specified value of 200, and the old indenter has a radius of 192 UM. The indenter with the larger radius has a greater resistance to penetration of the surfaces. Next we get figure 7.8, the micro hardness indenters. We get to figure also is a figure a schematic of the square based diamond pyramidal indenter used for the figure test, an example of the indentation it produces. B is schematic of the rhombohedral shaped diamond indenter used for the knoop test, an example of indentation it produces, and the indentation shown in the right side of both A and B were made in ferrite paste of ferritic martensitic high carbon version. Yep. Next we got 7.3 is a tensile testing. Next to hardness testing, mechanical testing of specimen under tension is by far the most common type of mechanical test that is performed. The properties derived from tension testing as described. A is stress strain curve showing the elastic and plastic strain regions of deformation under load. B, the tensile yield strain indicating when the elastic limit is reached with some appreciable amount of plastic deformation. And C, the ultimate tensile strength. For the first figure, we got figure 7.10 is the little giant hand crank tensile test of Tinius Olsen Tirta 1900. Next we get the big figure here. The figure 7.11 is the component of an electromechanical screw driven testing machine. For the configuration shown, moving the lower intermediate head upward produce tension in the lower space between the crosshead and the base. Then we get figure 7.12, the schematic of a basic servo hydraulic closed loop testing machine. And the last figure we get 7.13 is the example of gripping method for tension test pieces. A, we get round specimen with threaded grips, and B, butt and specimen constrained by split collar. C, we get gripping with serrated wedges, and D, we get seat specimen with serrated wedge strip. H region in C and D shows bad practice of wedges extending below the outer holding ring. Okay. Then we get to next slide, 7.4, fracture toughness. Plastic deformation in crystalline material occurs by process of shear. The actual measured shear strength of real engineering materials are often several orders to magnitude lower than the theoretical shear strength of perfect defect-free crystal structure. This discrepancy between theory and observation occurs because defect in the crystalline structure called dislocation. A similar analysis can be performed to evaluate the critical tension stress. And as we can see in figure 7.14, the test set up using wedge grips on the A figure, a flat specimen with axial extensometer, and B is a round specimen with diametral extensometer. Then we get figure 7.15 is a true thickness crack of length oriented perpendicular in the applied tension strength. The shaded regions surrounding the crack represents the material that carries little or no load to the presence of defect. At figure 7.16 we can see the SS schenectadly. After a sudden fracture due to rapid growth of crack that started in a whole wilt, the ships is cracked. And then we got to figure 7.17 and figure 7.18. The effect of thickness on the state of stress and fracture toughness at the crack tip, and at figure 7.18 the stress distribution ahead of a crack in which small scale plasticity is included. Then figure 7.19, the examples of specimen types used in the fracture toughness test. And the A figure is a single edge notch bend or SAB, and B is a compact specimen or CT. In the last figure we got figure 7.20, which I make also, is a specimen orientation seam showing the longitudinal low transverse and short transverse direction parallel to the rolling direction. Segregated impurities and intermetallics that lie in the planes represent easy fracture path, and the toughness is relatively low when the crack plane is perpendicular to these weak planes. The cohesion and crack tip blunting or stress reduction can occur. Effectively toughness the material, on the other hand, when the crack plane is parallel to the plane of this defect. Toughness is reduced because the crack can propagate relatively easily. Then we get next slide, impact 7.5, impact testing. Impact testing. In an impact test, the specimen is subjected to dynamic shock loading to evaluate the response of material to rapid change in loading, such as experienced by axle shaft when a car hit a chuck hole. A standard impact tester and its operation are illustrated in figure 7.21. 7.21, which I make there, is standard impact testing apparatus. When a specimen is placed in the path of the swinging pendulum, the pendulum must bend and or fracture the specimen if it should continue its arc. The amount of energy required to break the specimen is absorbed by the pendulum, which reduces the height to which the pendulum rises. The difference between the height to which the pendulum can rise unimpeded and the height to which the pendulum rises after breaking the specimen represent the energy absorbed in breaking the specimen. The two most common impact tests are the Charpy and ISO test. They differ mainly in the manner in which specimens are held and broken. Specimens over a range of temperature because some materials may exhibit a ductile to brittle transition at low temperatures. For example, only a small amount of energy is needed to fracture low carbon steel specimen at lower temperature. Next slide, we got 7.6, the fatigue testing. As we can see in figure 7.22 is the impact toughness specimen. We get two kind there is A Charpy and B the Izot. Parts subjected to repeated eye-leak stresses often fail in service even though the applied stress may be well below the strength of the material. We got figure 7.23, the laboratory simulation of the multi-stage fatigue processes, and 7.24, figure 7.24, the stress versus lock cycles to failure curve for bending and axial loading test of 4,340 steel. Then we got figure 7.25, the fatigue growth per fatigue cycle. Next, we get 7.7, non-destructive testing. First, we get table 7.2. Here, the relative uses and merits of various non-destructive testing methods. Then, as we can see there in the table, also we get next table, the table 7.3, the comparison of some non-destructive testing method. On a magnetic particle inspection is used to locate surface and subsurface discontinuities in ferromagnetic materials. The method is based on the fact when a material or part being tested is magnetized, discontinuities that lie in a direction generally transverse to the direction of the magnetic field cause a leakage field to form at and above the surface of the part. The presence of the leakage field and therefore the presence of the discontinuity is detected by used over the surface. Then we get figure 7.26, the liquid penetrant test for surface crack. A. An open crack draws a penetrant liquid by capillary action. B. The excess surface penetrant is removed. C. Developer draws out of penetrant liquid and form is a visible indication of the surface crack. Next, we get 7.27 is the electromagnetic yoke showing position and magnetic field to detect discontinuities parallel to a wheeled bed. Discontinuities across a wheeled bed can be detected by placing the contact surfaces to the yoke next to either side of the bed, rotating it about 90 degrees from position shown here. Next, we got next figure is figure 7.28, the effect of a crack on patterns on eddy current flow in a pipe. Eddy current inspection, as we can see in figure 7.28, is based on the principle of electromagnetic induction and is used to identify or differentiate a wide variety of physical, structural, and metallurgical conditions in electrically conductive ferromagnetic and non-ferromagnetic metals and metal parts. Eddy current inspection is used A. to measure and identify conditions and properties related to electrical conductivity, magnetic permeability, and physical dimensions, primary factors affecting eddy current responses, to detect seams, laps, cracks, voids, and inclusions, to sort dissimilar metals and detect differences in their composition, microstructure, and other opposites such as grain size, heat treatment, and hardness, to measure the thickness of a non-destructive coating on the conductive metals or the thickness on a magnetical metal coating on a magnetic metal. I think that's all I got. Thank you so much.